Hello everyone, and welcome to episode 5 of Let's Talk Physics. Today we're going to discuss what happens when you put a marble or any spherical object in a bowl. We're going to assume that the bowl is perfectly rigid and that the sphere rolls without slipping. And in particular, we're going to calculate how fast the sphere would be rotating when it reaches the bottom of the bowl after being released from rest at an angle theta to the central vertical axis of the bowl. There are two ways to figure out this angular velocity, and we'll start with the quick and easy one, conservation of energy. The sphere starts out with a certain amount of potential energy and ends up with less potential and more kinetic energy, some rotational and some translational. Even though the sphere rolls all the way down to the bottom of the bowl, the displacement of its center of mass means that it also has this linear component. We can represent this transformation of energy by saying that the change in potential energy is equal but opposite to the final total kinetic energy. Now, it helps to define our origin at the center of the bowl and axes positive toward the left and downward directions. This is so that we can have simple trigonometric relationships between x, y, and the distance between the sphere's center of mass and the center of the bowl. This means that our potential energy must be mgy, with g equaling minus 9.8 meters per second squared, so that the potential energy decreases as y increases. Now we can work out the change in potential energy and set that equal to the total kinetic energy. We know that a sphere's moment of inertia is 2/5 mr squared, and we also know that at any point, the linear velocity of the center of mass of our sphere is equal to the sphere's radius times its angular velocity. So we can make those substitutions and simply solve the resulting equation for omega, our final angular velocity. Now for the second method. This one involves rotational kinematics. We know that under constant acceleration, the final angular velocity squared equals the initial squared plus twice the angular acceleration times the angular displacement of the sphere. And let this angular displacement be phi since theta is our original angle of release. Since our angular acceleration isn't constant, however, we're going to have to integrate this from phi equals 0 to some final value of phi. To do that, we need to first find the angular acceleration in terms of phi, and we could do this using Newtonian mechanics, but it's simpler to use the Lagrangian method, which relies on energies instead of torques. First, we define our Lagrangian, which is the kinetic energy T minus the potential energy V. Now, to find the angular acceleration of our sphere, we need the entire Lagrangian to be in terms of phi, or its derivative with respect to time, which we would normally call omega. This isn't hard with our second term, since x dot squared plus y dot squared gives us the net linear velocity squared, and that's just r squared times phi dot squared. With our third term, we need to first get it in terms of theta. Recall that y equals L minus r times the cosine of theta, and then relate theta to phi. The distance our sphere travels along the bowl is equal to the bowl's radius times theta, but it's also equal to the sphere's radius times the total change in phi. This gives us the relationship that we need. Theta equals phi times r divided by L. This is the last substitution we need to make before solving the Euler-Lagrange equation, so let's get right into that. The partial derivative of L with respect to phi minus the time derivative of the partial of L with respect to phi dot all sums to 0. Now the partial of L with respect to phi concerns the second term, so we take our constants, multiply by the coefficients in front of phi, and multiply by minus sign of r over L times phi. Now the partial of L with respect to phi dot is 7/5 mr squared phi dot. And we add another dot from the time derivative. Now we solve the equation for phi double dot to find our angular acceleration in terms of phi. We can plug this acceleration back into our original integral, now knowing that our final value of phi is minus L over r times theta. Since it's spinning clockwise, the displacement has to be negative. We apply the same change to our sine function and factor out all of the constant terms. To clarify, we're switching the sign of L over r times theta and r over L times phi because we originally ignored the different directions of rotation to equate the scalar distances that the sphere traveled. Now, the integral of sine is minus cosine, and we multiply by minus L over r through the chain rule. We evaluate this at phi equals minus L over r times theta, in which case we get L over r times the cosine of minus theta, or equivalently times the cosine of theta, and subtract its value at phi equals 0, where we just get L over r. Notice that we can factor out this L over r and combine it with our other constant terms. The L cancels out with the L in the denominator, and the r in the denominator becomes r squared. Now, we just take the square root of this quantity, add a minus sign since we're spinning clockwise, and we've arrived at the same answer as before. That was definitely quite the long way around, but it just goes to show that more than one road leads to treasure, or something along those lines. So that's pretty much it for this episode, guys. I hope you enjoyed it, because it was a lot of fun to make. If you want to see me make any more videos or have any other thoughts, feel free to let me know in the comments below, and I will see you all next time.